One, here are the 9.2 notes for factoring using the distributive property. So quick review of 9.1. In the prime factorization of a whole number, each factor is a prime number. This means it can't be divided by anything other than itself and 1. In the prime factorization of a negative integer, all of the factors are prime except a negative 1. Now, why is that? Because negative 1 can always be broken down into 1 and negative 1, but negative 1 can always be broken down into 1 and negative 1. And if we were making a factor tree, our factor tree would go on forever. So negative 1 will always be our non-prime factor. So now we want to explain why the monomial 5x squared y is not in factored form. Well, this x squared is an exponent, and that exponent tells us it's not completely broken down. So if we wanted it in a factored form, 5 is a prime number, but we would have to break it down into x times y. So how would you find the GCF of 84 and 120? Well, the quick answer is the factor tree. The longer answer is what is the GCF, or the greatest common factor of those two numbers? Well, if I break it down here, I have 4 and 21, which breaks into 2 and 2, and 3 and 7. If I break 120 down, I'm going to break it down into 10 and 12, which is then 2, 5, 3, 4, 2, 2. What do they have in common? A 2 and a 2, for sure. And then they definitely have a 3 in common, but they don't have a 7, a 2, a 5 in that last line. So 2 times 2 is 4, 4 times 3 is 12. So the greatest common factor of these would be 12. It's the prime factors that when multiplied, they have in common. Well, what about the GCF of these monomials? These are a little bit trickier because we have to write them out in factored form to see how many of each thing we can take. T. 9 can be broken down into 3 times 3, so we'll break that out. And then x times a times b times b times t. This is just another method of doing the factor tree. What do they have in common? Well, they for sure have a 3 in common. They have an x in common. They have a b. And last but not least, they have these 3 t's. When we put that all back together and multiply it, we get 3xb t cubed. The rest is not the same. So the greatest common factor is that. So now let's look at distribution and how it applies to factoring. So we are really good at distributing. Basically what that means is we're going to take this term and multiply it by the first, and then we're going to take that term and multiply it by the second as well. So 2x times x is 2x squared, and 2x times 3 is positive 6x. Now when we distribute that in, what we did was we multiplied both of those terms by 2x, essentially making 2x a factor of those two pieces. Now, if we went the other way and pulled the 2x out, that would be the thing that they had in common. They both had a 2x multiplied, and now it's divided. Same thing here. When we distribute this in, what we're doing is multiplying each of these terms by this piece. So this is 4, a times a is a squared. There's no b, so we just bring that along. 2 times negative 5 is negative 10. And then we bring the ab along, so a. B times b squared is b cubed. Bring c along for the ride. And what we've essentially done is we have made 2ab a factor of those two terms. So what you should notice here is that 2ab is the greatest common factor. It's the thing that both of these two terms have in common when we divide it out. Same thing with our first example. Our 2x was our greatest common factor of our first term and our second term. All right, let's keep looking. Can we go the other way then? If we want to factor each polynomial, we need to figure out what they have in common. So 24 and 48. What is the largest factor that you can pull out of both? Well, 24 and 48, when we break them down, end up having a 24 as their greatest common factor. So what I'm going to do to factor this polynomial is I'm going to pull a 24 out of both terms. When I do that, I'm basically saying 24x divided by 24. What is left over is an x in the first term. When I pull a 24 out of my second term, I'm essentially saying 48 divided by 24 is a positive 2y. So all that's left when I divide 24 out of my second term is a positive 2y. Now notice, because I pulled the greatest common factor out of both, these two things no longer have anything in common. This is an x, this is just a 2y. If I hadn't pulled out the greatest common factor, these would still have something in common. For example, if I'd only pulled out a 12, I could have pulled out another 2. All right, let's keep going. We can also do this with 3 terms. Now, what do all 3 of these terms have in common? Well, unfortunately, these don't all 3 have something in common. So we're going to have to look at that one just a little bit differently. Why don't you try this one on your own? This one on your own before we get to something harder. All right. I hope you paused the video and tried this one. I realized I should have gone down instead of over, so I didn't want to jump over there as quickly as I did. My apologies for that. There we go. So what do 7x and 49 have in common? Well, I can take a 7 out of both of them. If I divide the first term by 7, I'm left with only an x. If I divide the second term by 7, I'm left with only a 7. Because these have nothing in common, I know that I have pulled out the greatest common factor of these two. Now let's go over to number 2 and see if we can do it with 3 terms. Notice all 3 of these terms have what in common? They have a single n. And that's all that they have in common. Even though this one has 2 n's, these two only have 1, so we can only take 1 out to be the greatest common factor. When we do that and we divide an n out of all 3 terms, we're left with 30 m n in the first term. Now, why did I put another n in there? Because when I divided n squared by n, I'm still left with 1n. What about in the second term? When I divide m squared n divided by n, I'm left with a positive m squared. In the last term, when I divide negative 6n by n, I'm left with only negative 6, because n divided by n is technically 1. Notice now, these 3 terms do not have anything else in common, so I know I have factored it completely. All right, let's see one more. What do these 3 terms have in common? Well, when I look, I notice they all have q's, but this one has 4, this one has 3, and this one only has 1. So because they only technically have 1 that I could take from the third term, I can only take 1 from the first and second as well. When I divide the first term by q, q to the 4th divided by q to the 1 leaves me with 3. When I divide negative 18q to the 3rd by q to the 1st, I get negative 18q squared. I've officially taken 1 from each of those. In the last term, when I divide it by q to the 1, I'm left with only 22 because q divided by q is just 1. So I know I've factored that completely. All right, I would encourage you to pause the video again and see if you can finish up the problems on this page. When you're done, come on back and we'll walk through them together. All right, I hope you paused the video, took a shot at both of those. Let's see what number 7 holds for us. What do the first and second term have in common? Well, I noticed that they don't have an h and they don't have any numbers, but they do both have a single t that I can take. When I divide the first term by t, I'm left with a single t and that h. When I divide the second term by t, I'm left with only a 3. I've taken it out, so I'm left with only that. On this last one, I noticed that they have a p in common, but nothing else. So I'm going to take the p out. When I divide this whole first term by p, the 3 remains. I'm left with 1 p because I only took 1. And I didn't take any q's, so I'm going to leave those alone. When I take p out of the second term and divide it out, I'm left with 6q. Now here's the tricky one. Remember, I'm taking p out, but what I'm effectively doing is I'm dividing. Remember, we're talking about factors here. So when I take the p out and put it out front, I'm essentially saying p divided by p, which gives me a positive 1. If I start with 3 terms, I have to end with 3 terms. So be careful not to lose that 1. All right, there it is for factoring each polynomial. Let me know if you have any questions.